start, sir.
So, a very good afternoon to all of you. Let me welcome you to the live session of this course on switching circuits and logic design. So, we are towards the end of this course, and I am sure many of you may be having some queries on some of the topics. So, let me pick up first some of the questions which were posted on the Google Docs that was shared with you. Well, one of you asked that are there any projects related to this course and what is the best course we can study after completing this? Well, in this context, let me tell you, this switching circuits and logic design, well, this is the name which is used in many colleges, but very similar courses exists in some other colleges with slightly different names. Like you will find courses with the names digital circuits, digital logic. They all are basically the same course with small differences here and there. So switching circuits, logic design, digital logic, digital circuits, they all refer to the refer to basically the same material. Okay. And this is one of the prerequisite core courses in the undergraduate curriculum of computer science and IT courses, of course, electrical engineering and electronics engineering. So this is like a common course. Now the question is, why do we need to learn this course? Well, this is one of the foundation courses that relates to digital hardware design. Well, let me take an example. For computer science students, there are other courses in the next semesters, in the higher semesters, like computer organization, computer architecture, microprocessors and microcontrollers, embedded systems. There can be many such courses. And this digital circuits or switching circuits, whatever we say, whatever is covered in this course, the basic gates, the way combination and sequential circuits are designed, they will form the foundation to understanding and learning and appreciating the topics that will be covered in those courses. So actually, when you are asking that what is the best course we can study after this particular one, I mentioned some of the courses which exist, but with respect to the courses under the SWAYAM NPTEL, there are many courses which you can try to uh, complete after this. Like I am just naming a few. There are courses on computer architecture, computer organization. There are multiple courses on these topics, you will see. Uh, there are courses on embedded systems. Embedded systems using ARM is one of the courses I am offering. And there will be some courses on VLSI design, physical design automation. So these are all courses which require this course on switching circuits or digital circuit as a prerequisite. So these are the subjects or courses you can take up if you're interested in this area. And regarding projects, well, you will find projects in abundance in these courses. Like for example, in VLSI, computer aided design, well, all the algorithms that we use, all the methods that we use for translating a specification into low-level description for VLSI fabrication, they all are very complicated and involved algorithms. So there is a lot of scope for developing and improving these algorithms, coming up with some algorithm of your own, building some prototypes, and so on and so forth. So there is a lot of scope. Uh, there is another question which is related. It talks about application-oriented problems in logic design. Well, application-oriented problem, as I told you, that logic design is a basic foundation level course. And when you look into computer architecture organization, let's say, when you design an adder, when you design a multiplier, when you design an arithmetic logic unit. So all the basic things you have studied in this course, they will be used there. So you can say that the design of a computer system is the best example application of these concepts that you are learning. So whatever you have studied here, they will be applied in the design of various digital systems for which system, a computer system is the best example. There you have so many digital functional blocks. There's a control unit, which is nothing but a finite state machine. It's a sequential circuit. So you need to know techniques to design and optimize such sequential circuits, which we have covered in this course to some extent. Okay. And there was one last course, it concerns the question type or the question pattern. Well, in the final examination, the kind of questions that you are expected to encounter will be very much similar to the ones you have encountered in the assignments. So those kind of multiple choice, uh, there can be a single correct answer, multiple correct answers. There can be fill in the blank type questions. So these types of questions will be there and it will be covering the entire syllabus. Okay. So the style of the questions will be not much different as compared to what you have seen in the assignments. Well, maybe some of the questions will be a little more challenging and it will be covering more or less the entire syllabus. And let me see if there are any questions on the YouTube chat. Yeah, there are a few questions. Let me try to just answer these. Markandeya Gupta, you have asked a few questions. Let me go through this one by one. What is the difference between digital electronics and switching theory and logic design? Well, as I told in the beginning, there is not much difference. In some curriculum, in some courses, this course is named as digital circuits or digital logic design. And typically in computer science curricula, this is called switching circuits and logic design. The only difference is that when you talk about switching circuits, so a little more detail about those finite state machines, minimizations, optimizations, those will be covered. In a classical course on digital circuits or digital logic, you will see that all these theoretical things are covered a little less. They deal with more with circuits, how to design a counter, how to design a register, using counters, how to design various different kinds of sequential elements, and so on. But in switching circuits course, we are also learning the formal mechanism. If we have the specification of a sequential circuit, a finite state machine, how to step by step design the circuit using whatever flip-flops are available with us. Okay, this is the main difference. The second question is, what are the extensions to this switching circuits and logic design course? Well, as I told you, that under this SWAM NPTEL platform, there are many courses. In fact, I have a few courses which are floated on a regular basis. I am naming a few. There is a course on computer architecture and organization. There is a course on embedded systems using ARM. There is a course on hardware modeling using Verilog. And there is a course on physical design automation. Now, all these four courses will assume knowledge about digital circuits, combination and sequential circuits, which you have studied as part of this course. Well, I have not mentioned about this course on Verilog. Verilog is also very important in, you can say, industries and the way things are designed today. Today, when we design a circuit, we do not really put it on a breadboard like what we used to do about 20 years back. Breadboard, connect them using wires and see whether it works correctly or not. We do it on a computer by writing a program. Whatever we want to design, we create a model of it. And there are some very standard languages like VHDL or Verilog. These are called hardware description languages. These languages can be used to model hardware. So once we have modeled our hardware, we can carry out analysis in various ways, whether functionally it is correct or not. Then there is a process of synthesis using which from that hardware description, we can come down to actually gate level or transistor level circuit, which can be implemented directly subsequently, either in the form of a VLSI chip or in the form of a field programmable gate array, which you call FPGA, and so on. Okay. There's a question, what are the applications of counters and what are different types? Well, Markandia, you see, we have discussed a few types of counters as part of this course. Let us try to understand what is a counter. Counter is something which counts. There can be an up counter, there can be a down counter. The up counter means which counts up 1, 2, 3, 4. A down counter is which counts down 4, 3, 2, 1. Let us look at some typical examples why we need these counters. Suppose you have designed some circuit which is installed at the entrance of a room near the gate through which people are entering. There is some sensing arrangement, a light on one side and some kind of light sensor on the other side, which will, that the light will be interrupted every time a person enters. So there will be a circuit which will be counting how many times these interruptions are taking place. So these interruptions are like a clock pulse. So if we have a up counter, which is initialized to 0, so every time a person enters, the count value will go up 1, 2, 3, 4, 5, 6. And if there is a proper display somewhere, you will directly know that how many persons are actually inside the room. Okay. Similarly, if there is another set of arrangement where you can detect whether a person is going out or not. So there can be an equivalent down counter. So when a person is going out, the count value will decrease. So in general, we are talking about an up-down counter. So whenever a person is entering, the count will increase. When a person is going out, the count will decrease. Okay, this is one example. Well, the second biggest example which all of us use is a digital clock. You think of the time on a clock, hour, minute, second. That is the best example of a counter. The second part, it starts with 0, it counts up to 59, right? After 59, it again resets back to 0. So it is a modulo 60 counter. It counts in decimal. Okay? We call it a BCD counter. Similarly, minute is also similar. Modulo 60 counter. From starting with 0, it counts up to 59. And hour, well, depending on the way you note the hour, it can go from 1 up to 12 or 1 up to 24. So these are all counters, different types of counters, different modulus. I am citing another example where you can keep track of time. Like I'm giving an example. Suppose I want to keep track of some event accurately with respect to time. Let's say I want to notify a circuit every 1 millisecond. Let's say every 1 millisecond. So what I can do, I can have a counter, a down counter, which I initially load with, let's say, the value 1000. And I feed it with a clock of frequency 1 megahertz. Well, 1 megahertz means what? 10 to the power minus 6 seconds. Every clock will be coming. So 1000 such clocks will mean 1 millisecond. Okay? Because one clock period is equal to 1 microsecond or 1 megahertz. Now, this is a down counter. So I design my circuit in such a way that the counter is counting down. Every time the count value reaches 0, I have a special circuit which can test for 0, maybe a large NOR gate with all the counter outputs feeding the input of a NOR gate. So output of the NOR gate will tell you whether the count of 0 has reached or not. So if it is 0, then you send the signal to that circuit where you want to intimate that 1 millisecond time has elapsed. And when this happens, you again automatically load the counter with the value 1000 and you repeat this process. So these are some of the applications of the counter, and there are in fact many different types of counters. I talked about binary counter. There is a BCD counter, which directly counts in decimal. There are gray code counters, and so on. Depending on what kind of code you are using to keep track of the count, there are various different ways of keeping track of code. Not only that, in the FSM design methodology, the sequential circuit design methodology that we had discussed, you have seen that if I give you an arbitrary transition diagram or a state table, from there you can design the sequential circuit. So I can design a counter which is not exactly counting up or down, but it can count in any arbitrary order. Let's say 1, 3, 5, 7, 6, 2, 0, like that. So whatever you give, the designer can design the circuit in a proper way by actually generating the functions for the different inputs of the flip-flops and minimizing them using a suitable technique, either Carnot map or tabular method or whatever. So if you have any other questions, you can ask. I don't see any other questions posted. Just you can ask any question. I mean, the questions may not always be related to this particular course. You can also post some questions which are not directly related. Now, while you think and post your questions, let me tell you a little bit about these hardware description languages. Now, in many of the courses nowadays, instead of doing this laboratory for this course in using actual circuits, well, of course, that is very important. You take a breadboard, you put the IC chips and other things, connect them together, apply a power and see whether it works correctly. That is, of course, something you need to know. But other than that, when you're designing relatively larger circuits, you should not have to break your head in designing a very large circuit on a breadboard and try to get it to work. Nowadays, these hardware description languages are very convenient. You can use them for designing or modeling a circuit, for minimizing a circuit, for simulation. Simulation means you have not designed the circuit, you have created a model. Now you're asking, well, if I apply this input 0101, what will be my output? So the simulator will actually analyze the circuit model and tell you what is the input output behavior. So you can actually see and verify whether the circuit realizes the functionality which you intend to implement. Okay. So that is what. So I'm waiting for questions. And just talking about the way you design circuits, well, for combination circuits, we talked about the basic functional blocks like your multiplexers, decoders, demultiplexers, encoders, and so on. So these are the basic building blocks. And for sequential circuits, you have counters and registers. But in general, you should know, we already worked out some examples that given any arbitrary specification, how to generate this circuit for a particular sequential specification. So through the process of state table minimization and then realizing the excitation function for each of the flip-flops, minimizing them, realizing them using gates or whatever, okay? Those are the ways. So if you have any kind of questions, you can post on the YouTube chat. Now for the switching circuits, the textbook on by that Kohavi, the, that that has been one of the oldest and one of the best books that is available on the subject. Because in Kohavi there is a mix of the actual circuit design thing and also the theory behind it. Because if you know the theory well, it becomes much easier for you to handle the design problem for complex circuits. Maybe you do not need to know everything that is there in the book by Kohavi for this introductory first level course, but it is always good to learn about the formalities, the formal techniques. So earlier the book was only by Professor Z. Kohavi, but subsequently one professor of Princeton University, Neeraj Jha, he actually modified the book. So now the book is available as Kohavi and Jha. So now the book has become much more, you can see, user friendly with a lot of problems and exercises. So now, basically, the book is now very useful for this kind of courses. And just another thing, let me tell you that when you design relatively complex systems, well, a computer system is the extreme example of a complex system. So you can forget that kind of a complex system. You can even think of a multiplier. I want to multiply two numbers. There are many methods of multiplication. Shift and add, Booth's multiplier, many methods are there. You will learn them. Now, for any such application, or say I'm giving an example, you want to design a circuit which will compute the GCD of two numbers, greatest common divisor of two numbers, which are stored in two registers. So you need a lot number of operations like subtraction, comparison. So you need a subtractor, you need a comparator, maybe you need some multiplexers. So all these functional blocks you are aware of. So to design this kind of a system, you need to work out in two different directions. One is you have to identify what are the functional blocks you require and how they have to be interconnected. That is called the so-called data path design. And the second thing is you will have to specify some kind of a you can say state transition table or state transition diagram kind of a thing. It is actually a finite state machine specification, FSM, where you specify how these different functional modules you have included in the data path, they will be activated to carry out the actual intended operation. So that FSM specification you are also telling. Now using the standard FSM synthesis techniques that you have studied, you can actually generate the circuit diagram for this control circuit. So now you have your whole circuit ready. One is your data path, which consists of the functional block. Other is your control path, it is called. And control path is activating the different blocks that are present in the data path. That is how large systems are designed today. Okay. So it seems that there are No further questions from anybody? Well, if there are no further questions, we can possibly stop today. Otherwise, if you have questions, we can discuss since we have time. Faizan, easiest way to prepare for exam, I would not say that you have to do anything special. For this NPTEL exam, go through the lectures, solve the assignments, and most importantly, understand the problems, that how they are getting solved in the assignments. So if you understand the concepts and how these problems are getting solved, so you will find that whatever questions are coming in the final examination, you will find it quite easy to tackle or solve. So it will not be much difficult. But the thing is that there may be some twist, a little twist in the problem statement. So if you have understood the problem, then it should not be difficult for you to come up with the right answer, the correct answer. Okay. So there is no easy way to prepare for examination, right? You have to understand and learn the subject. And if you understand the subject well, your examination performance will be good automatically. That is the idea. Let me see if there are any further questions or not.
Sir, you should wait 5 minutes. After 5 minutes, no question, then you can close the
Sure,
session.
sure. Okay. So possibly many of you are studying in your second year. You will be studying the so-called follow-up subjects in your subsequent semesters in your third and fourth years mostly. So you will see that whatever you have learned or studied in this course, they will be required or used in those subjects. Particularly in the subjects like computer organization, microprocessors, there you will find heavy use of these concepts. Okay. So understanding these concepts are very important because this is a first level basic course. So the other thing is that you don't only rely on what I have covered in the lectures or the slides. There are very good books available on the subject. Read the books. There are a lot of exercises at the back of the books. Try to solve them. Okay. They will be very helpful in understanding the concepts much better. So I think there are no further questions. In that case, we can stop the introduction section for today. Thank you very much for joining, all of you. Stay safe and do well in your future ventures, whatever you do.
Okay, sir. Thank you, sir.
Thank you.